We'll start in 5 minutes, please. Are you able to unmute and speak?
Yes, sir.
Okay, 5 minutes, we'll start. Yeah, let us start. Okay, let me share my screen. Is my screen visible?
Yes, sir.
Okay, thank you. Yeah, so where were we? What did we? Yeah, we did GMO ID methodology last class, right? So I also showed you the MATLAB, all those things. Any doubts in the GMO ID methodology? You guys have to practice. What do you say? I'll enable the assignment. Both, I think the first one also on LMS on the Takshila portal. So I think only when you start using it, you will recollect. Else, how much ever I speak, it will go above your head. Okay. So did I show how to use the MATLAB files and draw the curves last time? Was that understood? I'll share all those files as well. I'll upload the assignment as well. Okay. So this is sweeping. Yeah. Everything looks good. Yeah. Any doubts in GMO ID methodology? So we'll be applying the same GMO ID methodology, but on different circuits. I think in the previous class, we solved this problem. Okay. Common source amplifier with a resistive load. Okay. So in this class, we will look at a different circuit. Okay, but the GMO ID methodology remains the same. The philosophy of the GMO ID methodology remains the same. So we have simulated this circuit, a diode connected load with a current source. So we have varied the current source from nanoamps to milliamps, and we have plotted different parameters here: GM by ID, GM by GDS, GM by CGS, ID by W. So these were the parameters that we plotted. The reason being, we understood. So from the discussion before that, we concluded that these are independent of width. Okay. So the main reason being, we wanted to cut down this simulation, which is nested four for loops, into this simple simulation. Okay, with only two for loops. So that is the advantage that we get with this GM over ID methodology. So if we consider parameters like GM, GDS, ID, and CGS, so the simulation loop, the solution space, in order to get the solution space, you have to run a big nested for loop, almost four for loops. But rather, if you consider these parameters which are independent of width, okay. So if you run only this one nested for loop, one level, so you'll get the solution space. From that solution space, we plot these GM over ID with other parameters. Suppose we plotted GM over ID versus ID by W. Okay, so I think I see it here. See, this is GM over ID versus VGS in order to get the bias. GM over ID versus ID by W. From this, we got the width value. Okay, and that was enough. Okay, so today we'll see a different circuit as well. Okay, so let me go ahead. Page. I think this is lab 1, 2, 3, 4. Is it lab 4? Okay, so Naveen sir took one lab. I took one on cadence, another on GM over ID. This is third one. So overall fourth one. Yeah, fine. Yeah. So today we will take another circuit, maybe which includes PMOS as well. So we weren't looking at PMOS in the previous class. We sized only NMOS, right? So today we'll go ahead with a PMOS circuit as well. Okay. So let me go with this circuit. So common source amplifier.
Sir,
Yeah, please.
sir, in the previous lecture, right? So when we plotted the graphs in the cadence, then you showed in a MATLAB. So do we have to know the conversion from this cadence to MATLAB, or we'll get it ready-made?
I'll give you everything, but you have to understand that cadence curves are different from MATLAB curves. I told 2, 3 times also last class. Remember?
Yes.
Okay. See, the circuit remains the same. Whatever may be the problem at hand. Okay. So whatever may be the circuit. Okay. The curves that you get are from this circuit only. This one. Right? Are you able to see?
Okay.
Okay.
Yes,
So
yes.
if you are working in cadence, you will be using what? Which technology were you using? GPDK 180. Yes or no?
Yes.
If you are using LT Spice, what is the model file that we were using?
Same, right? 180.
180, but TSMC 180.
TSMC, TSMC, TSMC. Yes.
GPDK 180 is different from TSMC 180. Okay,
Yes.
GPDK is some educational purpose PDK given by Cadence so that students can learn about different things. But TSMC 180 is from the foundry itself, although it may be very old, from 90s or early 2000s. It is a bit old, but it is a commercial PDK, TSMC 180. Okay, so have this distinction in mind. If you are using Cadence, you are working on GPDK 180. If you are using LT Spice, you are using what? TSMC 180. Okay. See, Cadence simulator is advanced. So it can plot even all these advanced things, right? GM by ID versus ID by W, all these advanced curves we plotted, wave versus wave features, all those things are available in Cadence. Okay. But LT Spice is also commercial, not so commercial. It is open source, but it doesn't have these advanced features. Okay, so what I told you, I imported the TSMC 180 file into the Cadence. I performed this simulation in Cadence for TSMC 180. I got all these CSV files for TSMC 180, and then those CSV files I imported into MATLAB and plotted the curves. Is that clear? Okay.
Yes, sir. Clear. Yes.
Okay, so you can use both Cadence and TSMC, sorry, LT Spice. If you are using Cadence, use the Cadence internal feature. You can use the wave versus wave, all those things, right? Use those and then get the different curves that you want, GM by ID versus ID by W, all those. If you want to use LT Spice, remember the MATLAB, okay, the MATLAB files, whatever I have done the background work for you. I am giving you the curves on a platter. Okay, so why is this made possible? This is made possible because the solution or the curves are generated with a single circuit itself. Okay, whatever may be the circuit that we want to apply the GMO or ID methodology on. Okay, the solution space remains the same. This is the solution space. This circuit, whatever is the outcome, whatever is the analysis, whatever this procedure that we are doing. Okay, so this is the same solution space. So the solution space doesn't change with the circuit. The circuit may be common source amplifier, common drain amplifier, common gate amplifier, cascade amplifier, whatever it may be. Okay, the solution space is only from this single circuit. Is that clear? So that is why GM over ID methodology was possible even with LT Spice plus MATLAB. So whatever features that LT Spice doesn't have in terms of plotting, we are using and leveraging MATLAB features in order to get those plots. That's it. So we are making LT Spice as close to Cadence with the help of MATLAB. That is what we are doing, nothing else. Okay. In fact, TSMC 180 is supposed to be a better PDK compared to GPDK 180. Okay, because it was a commercial PDK which was made open source. In the late 2000s, it was made open source. Okay. Right. Is that clear? Is that distinction clear for everyone? That is very, very important. If you can apply the methodology in both Cadence and LT Spice. If you are using Cadence, the GPDK 180 nanometer related to that particular wave curve fitting, whatever model fitting algorithm is given in Cadence, you get that. If you are using LT Spice plus MATLAB, you will be using TSMC 180 nano, and you get the curves according to that. Is that clear? So either is same. Whatever you use, now the solution, you have the solution space in your hand. Okay, if you want to use Cadence, good luck. If you want to use LT Spice, good luck. Everything, the methodology remains the same because the solution space is generated with a single circuit. Be it Cadence, if it is Cadence, we generated the curves with this, but the PDK is GPDK 180. If it is LT Spice, we generated the solution space with the same circuit, but the PDK is TSMC 180 nanometer. I generated all the curves in the backend. I am giving you the MATLAB code so that you don't have to every time do this. Okay. In fact, I'm making things easier for you. Okay. Is that clear? Is that distinction clear?
Yes, sir.
That is very, very important. Okay. Right. So shall we proceed? So we will go ahead with, okay. Yeah, common source amplifier with an active load. Okay. So we all know this. We have beaten this to death. Okay. But one small factor comes over here, which is current mirror, that you have to agree with me. Okay. Because we haven't started current mirror yet. Ideally, it would start next week because we are done with the. Okay. So this is Wien. Now, because I am talking about an amplifier design, two important specs, okay, to be considered for every amplifier. One is the DC gain, the other is the bandwidth. Okay, so when I am talking about the bandwidth, the load capacitor has to come into the picture. So CL, Okay, so this frequency picture, everything we will see once we are done with current mirrors. I will deep dive into the frequency picture as well. Okay, so it will be again completely mathematical, but it will be only algebra, like I told. You won't have any complex vector mathematics or vector calculus. Okay, so don't worry about it. Okay, so this is the common source amplifier with an active load. So this is the an active load which is biased to be in saturation region so that it acts as a constant current source. So we replaced RD with a constant current source basically. Okay, so this is not diode connected load for obvious reasons. Diode connected load, I lose my output swing. Okay, so 1 VTH extra I lose. Even when Vin is equal to 0, output cannot be VDD. It will be VDD minus VTH. All that discussion is done. We have seen that in so much detail. Okay, right. So if we draw the small signal for this, so this is, I think this may be the last time I'll be drawing, but this is V in. So this is the gate. Okay. So this is GM1 times V in. So let me use GDS here. Okay, which is the channel length modulation parameters. Okay. So this is V out. This is my load capacitance. And looking through this terminal, this is nothing but GDS2. Okay, and this is ground. This is the CLM parameter of the PMOS. This is the CLM parameter of NMOS. Okay, both don't have body effects. NMOS is grounded, no body effect. PMOS is connected to VDD, no body effect. Okay, so this is the small signal equivalent. Instead of R01, R02, I am writing GDS1, GDS2 because we have seen in cadence that the tool is providing GDS1, GDS2 in those small signal parameters. It was giving these CLM parameters as GDS1 and GDS2. GDS1 is simply 1 by RDS1. That's it, transconductance. 1 by R01 and GDS2 is 1 by R02, as simple as that. Okay, there is no what do you say, rocket science over here. Okay, right. So again, let us proceed. We apply KCL over here because we have a capacitance over here. I am deriving it again. So again, so this is a leaving current. Let me suppose this leaving current, suppose let it enter in this fashion. Okay, and then suppose this is also some entering current. Okay, so I have given my directions over here. So the leaving current is GM1 V in. So this is equal to, okay, so 0 minus V out divided by RDS1. So 1 by RDS1 is GDS1. So 0 minus V out into GDS1. So this current, okay, plus this current, 0 minus V out into GDS2 plus this current through the capacitance. So this is 0 minus V out divided by 1 by SCL. Okay, so the reactance of the capacitance is XC. XC is nothing but 1 by j omega CL in the Laplace domain because we are in the Laplace domain. So that j omega is replaced with S. So this becomes 1 by SCL. So if you want to do it in time domain, okay, good luck to you. You will go into the differential equations and it is very difficult. At least for me, it is very difficult. So if I rearrange things, so that is if I calculate V out of S by V in of S, so that is what I get minus GM1 divided by, okay, so GDS1 plus GDS2 plus SCL. Okay, we didn't have this capacitor previously and we got this one as the DC gain, GDS1 plus GDS2. So this we wrote as minus GM1 RO1 parallel RO2. Okay, so these two are one and the same. These two are one and the same. Okay, so this is called as the, what is this called as? Anyone? I told you last time. What is this called as? This is the transfer function. Okay, Right. From this transfer function, what is DC gain? Anyone? How do we calculate DC gain from the transfer function?
Final values. Put S
What is the frequency of DC?
0.
Omega is equal to 0. What is the frequency parameter in this thing? So substitute S is equal to 0. So if you substitute
Yeah.
S is equal to 0, what do you get?
The GM into R naught per R.
Or the same thing
Yes.
in a different format. Different format. Okay. So this is equivalent to minus GM1. Okay. So this we have seen. So this is a little new to us, but mathematically both are equivalent. Okay. Right. So from this transfer function, what is the order of the transfer function? So look at the denominator. What is the highest degree of S term?
1.
Okay. So which order is this transfer function?
First order.
First order transfer function. Okay. I'll slowly introduce from controls concept. Okay. Not control. So this is first order transfer function. Okay. Right. So minus GM1 divided by GDS1 plus GDS2 plus SCL. Okay. So from this transfer function, what are poles and what are zeros? You would have heard of these things. Transfer function is of the form numerator by denominator. And numerator is a polynomial in S. Denominator is also polynomial in S. So in the numerator, what do I have? Only the constant term. Okay. I don't have any terms related to S. In the denominator, what do I have? GDS1 plus GDS2 plus SCL. Okay. So what are poles and what are zeros? Anyone would have done this?
Pole
The
is
roots.
minus GDS1, GDS2.
So the roots of the denominator polynomial are called as what? The roots of the denominator polynomial are called as poles, and the roots of the numerator polynomial are called as zeros. Okay. So do I have any zeros from the transfer function? So this is my transfer function. Do I have any zeros in the transfer function?
No.
Yes. No. Okay. So there are no zeros in this circuit. Okay. Are there any poles? What about poles?
Yes.
Okay. How many poles are there? First order transfer function.
One pole.
One pole. Where is the pole?
Minus
Root.
GDS1 minus
Very good.
GDS2 by CL.
Very good. Very good. So you have to solve for S. When I said root, you have to find out. So what I mean is x plus a is equal to 2. Find out x. So x is equal to 2 minus a. X is the root. So similarly, you have to calculate for S here. What is S equal to here? Minus GDS1 plus GDS2, the whole thing divided by CL. Okay, right. So where is this pole line? Where is this pole line? The GDS is a positive value, GDS2 is a positive value, CL is a positive value. So on the S plane, so this is called the S plane, this is sigma and j omega. Okay, on the S plane, it is on which side? Is it on the left half plane or the right half plane?
Left.
Yeah, the pole is, S is a negative value. So the pole is on the LHP. Okay, so if the pole is on the LHP, what can you say about the transfer function? It is bibostable, yes or no? You have to recollect your controls. Control engineering or control systems, whatever that subject you may have studied. Okay, you have to recollect all those. Okay, so this is a bibostable, bounded input, bounded output stable transfer function, and the pole is indeed on the left half plane. And the pole frequency is nothing but omega p. The pole frequency is GDS1 plus GDS2 divided by CL. This is the pole frequency, omega p1. There is only one pole. Okay, right. So in the previous class, we have seen the bandwidth. What is the bandwidth? Bandwidth? The frequency at which, the
Gain drops
frequency
by
at
3
which,
dB. Hmm.
yeah,
DC gain becomes 1 by root 2.
yeah, the magnitude of the DC gain becomes 1 by root 2 DC gain. So that is nothing but the bandwidth. Okay. So today we will introduce another frequency term called as omega u, which is nothing but unity gain frequency. Is nothing but unity gain frequency. What is unity gain frequency? The frequency at which the magnitude of the gain is 1 or 0 dB. If you are talking in terms of 20 log V0 by V1, okay, that axis you are using, then 0 dB, log 0 is 1, right? Okay, so 0 dB, or sorry, log 1 is 0, not the other way around. Sorry. Yeah. So if you are talking in terms of V by V, it is when the gain becomes 1, or if you are talking in terms of decibels, when the gain cuts the 0 dB axis. Okay, so that is the unity gain frequency. Okay, right. For a typical first order system, I know it is going into controls domain, but yeah, it is very important because you are designing a system at the end of the day, so you can't escape control systems. So typical first order system without any zeros and one pole. This is what we are talking about. From the transfer function, we have seen that. Okay, so how will the magnitude and phase plots look like? So let me try to draw. Let me take a better color. So let me go ahead with the magnitude plot. So this is the frequency. This is the magnitude. The magnitude is in decibels, 20 log mod V0 by Vin. Okay, so this is the 0 dB line. The x-axis is nothing but the 0 dB line. Okay, let me take some other color, some blue color. Okay, so typical Bode plot. Okay, this is called as a Bode plot. So Bode plot is itself again an approximation. Okay, Bode plot is itself an approximation. So this is how the typical Bode plot looks like. So it starts with the DC gain, and at the pole frequency, what happens to the magnitude plot? See, the DC gain here is 20 log mod minus GM1 by GDS1 plus GDS2. That is where it starts at DC. That is the gain. So it will be more or less the same until the pole frequency. Okay, so this is my pole frequency. What was my pole frequency? What did I calculate it as? This was my pole frequency. At this frequency, pole occurs. So after the pole, what happens to the magnitude plot? Anyone? Do you remember your Bode plot?
Gain drops
Gain drops by how much?
20 dB per decade. Minus 20 dB.
Yeah, very good. Gain drops by, or gain goes down by 20 decibels per decade. Okay, and it goes down and down, and it ultimately touches one point. What is the gain over here?
Gain is 1.
Gain is 1 or 0 dB. So what is this by definition? What is this frequency?
Unity gain.
Unity gain frequency. So this is the unity gain frequency, and this is my bandwidth. Okay, so at the pole itself, okay, typically at the pole, so the gain becomes equal to DC gain by √2. But that transition we don't show. Bode plot is rather an approximation, right? Okay, since this is only a smaller approximation or a small variation, we take it as minus 20 decibels per decade. Okay, so please try to recollect your Bode basics, Bode plot basics. Okay, so yeah, right. So this is the typical magnitude plot. This is the typical magnitude plot of a first order system with one pole and no zeros. Okay, so there is also, of course, the phase plot. Okay, so let me also come up with the phase plot. Okay, see, this is very important. I'm not trying to deviate or anything. Very, very important. If you are designing amplifiers, you can't escape Bode plots. Okay, I'm not deviating at all. Don't think that I'm teaching something else. Okay, so this is my frequency axis. This is my phi. Okay, so the phase. So at DC, what is my phase? At DC, what is my phase?
It's a negative sign, right?
Negative sign. So
180.
very good, excellent. Very good. You must be in analog domain. You're answering well. Okay. So it starts with 180. Why? Because it already has a negative sign. Okay. Right. So how does the phase behave? So every pole. Okay. Let me write down here. Every pole causes a minus 90-degree phase shift. Okay. Every pole causes a minus 90-degree phase shift. But at the pole frequency, it is 45 degrees. It is minus 45 degrees. Okay. So minus 45 occurs before the pole. Minus 45 occurs after the pole. That is what I mean to say. Okay. So let me try to draw it here. Okay. So this is the pole frequency. So let me continue with that. So what I mean to say is ultimately there will be 90-degree phase shift. So that means you will go from 180 to 90. 180 minus 90 is 90. Ultimately, there will be 90-degree phase shift because of this pole, but it will be exactly minus 45 at the pole frequency. So that means at the pole frequency, it will be 135 degrees. Okay, so let me try to draw this. Let me try to draw this. Okay, 45-degree phase shift happens before the pole. The other 45 happens after the pole. Is that fine? This is how the phase plot looks like. This is how the phase plot looks like. Anyways, after we do the AC analysis today, I'll show you the phase plot also and how it is varying. Is that clear? It is the Bode magnitude plot and phase plot and the unity gain frequency. So this is my 0 dB line, which is 1 V by V. Okay. And this is my pole frequency, omega P. Okay, I could have done a better job. The phase plot doesn't look like this, but you get the idea. So because of one pole, there will be a 90-degree phase shift, 45-degree at the pole frequency. So that means 180 to 135 phase shift happens before the pole. 135 to 90 phase shift happens after the pole. That is what I wanted to convey. My diagram is a bit off. Okay. Okay, is that clear? So this is how the Bode plot looks like, both magnitude plot and the phase plot. Okay, right. So where were we? We had the transfer function. Okay, minus GM1 by GDS1 plus GDS2 plus SCL. Okay, right. So let us calculate the omega u. Okay, for this particular transfer function, let us calculate the omega u. Okay, so let me start over. So where did we start? V out of S by V in of S. Okay, minus GM1 divided by GDS1 plus GDS2 plus SCL. Okay, so from this, calculate omega u. So omega u occurs when this mod V out of S by V in of S, this becomes equal to 0 dB or this is equal to 1. Okay, so this implies what? Mod of minus GM1 divided by GDS1 plus GDS2 plus SCL. This has to be equal to 1. Okay, right. So I rearrange this stuff over here. Anyways, mod is there. So that negative goes out of the window. So if I am rearranging this here, GDS1 plus GDS2. So this is nothing but the DC gain part. Okay, by 1 plus SCL divided by GDS1 plus GDS2. Mathematically, these two are the same. Mathematically, these two are the same. So calculate the LCM and these two cancel out and you'll end up with the same. So this is simple mathematical manipulation that I have done. This is a simple mathematical manipulation that I have done. Now, if I rearrange this equation, okay, what do I have? GM1 by GDS1 plus GDS2. I'll multiply this to the other side. So this becomes mod of 1 plus SCL by GDS1 plus GDS2. I still have mod here. Why? Because S is there. S is nothing but J omega. I still have that complex number over here. That is why I still have mod. If I have to calculate the mod, you know that if A plus JB, mod A plus JB is under root A square plus B square. Okay, I still haven't invoked that. So that's why I'm still calculating that over here. So let me replace S with J omega. So this will be J omega CL by GDS1 plus GDS2. So now I'll apply that formula. Mod A plus JB is under root A square plus B square. So GM1 by GDS1 plus GDS2 is equal to under root 1 square plus this omega is nothing but omega u now, isn't it? So this is omega u square CL square divided by GDS1 plus GDS2 the whole square. Okay. So I'll do a small approximation. We are all engineers. We love approximation. So this is a pretty high value. So adding it with one, okay, will not fetch me anything insightful. Okay, no insight can be drawn out of this. So I'll approximate this. Okay. So I'll approximate this as this omega u square CL square divided by GDS1 GDS2 the whole square. Okay. Overall, my aim is to calculate omega u. Okay, so if I am rearranging GM1 by GDS1 plus GDS2 is equal to omega u CL by under root everything whole square. So the square gets cancelled. GM, these two get cancelled. So omega u is GM1 divided by CL. So the unity gain frequency is GM1 divided by CL. Okay. So this would be, of course, in what? The units will be radians per second. If you want in hertz, this will be 1 by 2 pi times GM1 by Cl. This GM1 is important because this is the transconductance of my NMOS. GM2 means transconductance of a PMOS. Okay, here NMOS is my input device, PMOS is my load device. Okay, so the unity gain frequency is dependent upon my input device, not my load device. So that is why that GM1 is important. Okay, so this FU will be in hertz. Okay, right. Okay, okay, right. So how the actual circuit looks like is the biasing happens with a current mirror. Of course, we haven't done current mirror. Okay, but you will understand in the next week, we will be dealing with current mirrors in and out. Okay, so how the actual circuit looks like. So this is biased with a current mirror actually. So this is some reference or bias current. So there will be a circuit called band gap reference. Those who are in analog domain might already know. So from the band gap reference, we get these current sources. Okay. So this is designed to tolerate variations. Okay. So your VDD or DC voltages or DC currents that we assume. Okay. So this VDD and this IREF are given out by this band gap reference. Okay. If you take an advanced course in mixed signal design, or if you do a mixed signal design course, band gap reference design is also taught. Okay. So there you will see. Okay. Anyways, you have to take that. I have a circuit block. What I'm trying to say is I have a circuit block which is resistant to different temperature and other variations, and it remains pretty constant through any type of variations. So this block of circuit is already present on my IC. I am using it for my purposes, for biasing purposes. Okay, so this is the bias circuit that I was talking about. So this is a PMOS. This is M1, this is M2, and this is M3. So what happens in a nutshell is, see, this M2 and M3 both are in saturation. Okay. So this IB will be equal to IREF in a nutshell. Okay, because VGS3 of both of these is, or VGSs of both these M2 and M3 are constant. The current will also be constant. That is the overall concept behind the current mirror. But don't worry, you can take it from me that in today's class, this is how the biasing is done for this in the saturation region. Okay, but in the next class, I will go in very detail and explain how M2 and M3 form a current mirror. Okay, right. But today you take it from me that this is the current mirror, because if I start explaining current mirror, the focus is lost on the amplifier. So that's why I am not doing this. Okay, now, right now. But next week, our topic is current mirror only. I'll go in very much detail. Now, let us take the design problem. Okay, I'll say design a CS amplifier with an active load. Okay. So minimum current gain, minimum voltage gain I am looking for is NV by V. Unity gain frequency, not radians per second, but in hertz. I want suppose 100 megahertz. And suppose my load capacitance is 1 picofarad. Okay. So bandwidth requirement in terms of unity gain frequency is given. Okay. Gain requirement is given specified directly. AV is minimum gain is 10 V by V is what I'm looking for. Okay. So let us try to size this. Okay. And I'll be using my GM over ID methodology. in wherever necessary, and I will do the design. So the end goal is get the sizes of M1, M2, M3. Okay. So that I meet the specifications. In a nutshell, that is what I'm trying to do. Okay. And one more point here. If this has to be a current mirror, then M2 has to be equivalent to M3. Okay. So that also one point you keep it in mind. So that means whatever are the sizes of WL of M2 will be the same for M3 as well. Okay. So keep that in mind. Okay. So if we size M2, we are sizing M3 also. Okay. So that is what I want you to keep in mind. Right. So let us proceed. So we can start with the DC gain. What is my DC gain? Anyone? So GM1 divided by GDS1 plus GDS2. I am telling minimum of 10. Okay. So here I'll make a small assumption. So I will say that the channel length modulation parameters of both NMOS and PMOS are equal. Okay. And let it be some GDS. Okay. So what will this become? GM by 2 GDS. Okay. Which has to be 10. So that means GM by GDS is 20 because it is minimum. Okay, so it has to be greater than 20. So I'll choose a GM by GDS of 25 to be on the safer side. Okay, you can choose any value, 23, 24 is also fine. Okay, just some round number I wanted to take 25 because I told you that this is the minimum gain. So I wanted a value greater than 20. So I am choosing GM by GDS as 25. Okay, right. Now I also have FU, the unity gain frequency in Hertz, which is 1 by 2 pi times GM1 divided by CF. Okay, right. So FU is 100 megahertz. So 100 into 10 power 6 is equal to 1 by 2 pi into GM1 divided by what is load capacitance? 1 picofarad. That is 1 into 10 power minus 12. So from this, I can easily calculate GM1. Anyone can help me with GM1? Can you rearrange this stuff and tell me? So I got this 628 microsiemens. Do you guys agree with me?
Yes, sir.
Okay. So you got, I think, similar values. You would have got the similar values. But what is my required GM1 by GDS? What is required GM1 by GDS? What did we take here? Look at this
25.
value. 25. So from this, I can calculate GDS. What is GDS? Yeah, not Siemens. 25 micro. See, 25 into 25 is 625, right? Yeah, roughly I can say that this is 25 micron GDS. Yes or no? Hey, now I will go to my curves now. Okay. So the first curve I will be looking at is GM by GDS versus GM over ID. Okay. So what is the value I have to look for in GM over GDS? This 25. Okay. So for 25, I get some value X. Okay. So I know that GM1 by ID is equal to X. So what will ID be equal to? GM1 by X. So I found ID value. So I have calculated ID now. I got the ID value from this curve. GM1 by GDS versus GM over ID. Okay. I got the ID value. Okay. So let me open MATLAB and then show you. So that parallelly. Are you able to see my MATLAB? Or the are you able to see my browser?
Yes, sir.
Okay. This is easier and faster. That's why I'm showing you MATLAB. You can do the same in Cadence also. I'm not stopping any one of you to use Cadence. Okay, so this is my transistor suite I have done. This is in a different folder. So it was asking, so which browser do I have to go? What is it that I am trying to look at? GM1. GM1 means NMOS, right? Which browser do I go? NMOS or PMOS?
NMOS.
NMOS. Okay. So in the NMOS, what is the curve that I was looking for? GM by GDS versus GM over ID. See this one. Okay. So suppose I want to do it for 180 nanometers itself. I don't want anything else. Okay. So I'm doing it for 180 itself. What is the value of interest? Which GM by GDS am I
25.
looking for? 25. Very good. So at 25, what is the value of GM by ID? Roughly
4.88.
4.88. Okay. What is my X? X is equal to 4.88. So from this, if I reverse calculate, GM1 by ID is equal to 4.88. So ID is equal to GM1. What is GM1? So what is my ID? Anyone can help me with this? What is the ID value? 130 micro, around 15 fours or 60, right? So somewhere between less than 150 micro. What is the exact value? Anyone can help me with this?
128.68. 128.
Okay, I will take 128 micro. Fine. So I calculated ID. Now I have to get the width. Okay. So I'll go ahead with GM over ID versus ID by W. Okay. What value of GM over ID am I looking for?
4.88.
Very good. From this, I'll get some value for ID by W, some Y. Okay. So W will be equal to 128 micron divided by Y. So that will give me the width. So let me go back to my curves. What do I want? GM over ID divided by I versus ID by W. See, which nanometer are we looking for? 180 nanometer. And GM over ID value is 4.88. This is somewhere here. 4.88. What is the value? 82.9 or 83. I can take it as 83. What is my Y value is 83. So width is 128 micron divided by 83. Can anyone help me? 1 point something. What is the exact value?
1.54 micro.
Okay, pretty good. Pretty good width. Okay. And remember, there has to be some bias voltage here, right? VGS, for this to be in saturation. Okay. So what curve do I look out for? GM over ID versus VGS. Okay. Go back. GM over ID versus VGS. What is the GM over ID of interest for me?
4.8.
Very good. Very good. Very good. 4.88. How much is VGS? Nice value.
0.8.
0.8 volts or 800 millivolts. Okay. So my VGS is 800 millivolts. Is that fine? Are you able to follow? Okay.
Yes, sir.
Then we have to size the PMOS. I told you M2 and M3 both are what do you say, equivalent. So if you size M2, the same you apply for M3 as well. IREF we calculated. So IREF will be equal to this bias current. What is the bias current that we got? ID from this 128 micron. Okay. Right. Now we have to calculate the width and length of M2 and M3 so that we meet the required spec. The spec we have already taken. Minimum gain and unity gain bandwidth. Okay. Right. So for this, we take a unique, what do you say, curves. Okay. So which is nothing but GDS by ID versus ID by W. So GDS by ID versus ID by W. So this we are sizing PMOS, right? Okay. Yes or no? We are sizing PMOS or NMOS?
PMOS. Sir, because we
PMOS.
know ID value, that's why we do. And GDS is half, right? Means both
Yeah.
having same GDS. That is what assumption.
So
That's
if I
why.
take
Okay.
GDS by ID by W, am I doing right thing or wrong thing? So I need PMOS currents. This is NMOS currents, right? So I'll close this, go to PMOS browser. Okay, understood, right? So I go to GDS by ID versus ID by W. So I am worried only about 180 nanometers. So I'll click on the other things, though they go away. Okay, so what is the GDS by ID of interest for me? What is GDS I calculated? GDS2 is equal to GDS is 25 micron. So this is 128 micron. How much is this? Okay, so I see I'm trying to calculate GDS by ID, which is 25 micron by 128. So 195. I'll take it as 0.2.
Yeah, 0.2 is fine.
0.2. Okay. 0.199. 0.2. At 0.2, what is the ID by W? 8.29 or 8.3. Okay. So at 0.2, ID by W is equal to 8.3. So what is W equal to? ID by 8.3, which is 128 micron divided by 8.3. Anyone? What is the value of width?
15.4 micro.
Okay, this is good. I can go till, I think the width as high as 50 micron. I am fine. Okay, 15.4 micron is well within my limits. Okay, the tool will allow also, the cadence will allow it as well. Okay, right. So M2 is identical to M3. Okay, so this is 15.4 micron. This is 1.5 micron. IREF is 128 microamps. So this is same 15.5 micrometer. This is micrometer. This is microamps. Okay. So it is done. Now I have to verify it. Now I have to verify it. So I'll plug in the circuit in LT-Spice because I have done it from MATLAB. I want to use in LT-Spice. It is faster as well. Okay. Again, I am not discouraging you from using Cadence. If you want to use Cadence, it is the best tool, best commercial tool available. So go ahead with the Cadence as well. but the procedure remains the same. That is what I am trying to say. Okay, right. So yeah, so this thing is actually in another PC in my Mac. Okay, let me connect my Mac. Please give me 2 minutes. Yeah, am I audible? Am I audible? Can one of you please confirm? Is my screen visible?
Yes,
Am I
sir.
audible? Yeah.
Yeah.
Okay, thank you. I thought Mac was okay. I did it Mac. Okay, right. So are you able to understand the circuit? So this is the input MOSFET NMOS. So this is the current mirror, two PMOSes. So these two are connected to VDD. I used a label VDD so that the connections won't be clumsy. So the substrate of PMOSes are connected to VDD. Substrate of NMOS is connected to ground. So this is my output terminal, and load capacitance I have given as 1 picofarad. Okay. So this is my TSMC 018 library. See, I am using two sources here. So one is the DC source, which is 800 millivolts that we calculated, that VGS was required for this MOSFET to be in saturation. And another voltage source, which we take it as AC amplitude as 1, because we have to run a AC analysis. So this is the AC analysis. So this is going in decades. That means it goes in multiples of 10. So it starts from 10 and goes to 1E9, that is 10 power 9 hertz. 10 power 9 hertz is 1 gigahertz. So it goes from 10 hertz to 1 gigahertz in multiples of 10. So that is what this directive is all about. Okay. And this is my reference current. See, I got some 123 micron. Okay. So, and what is 1.55? This looks fine, right? We also got 1.55. The NMOS, the PMOS, I got 15.5. I used 15.5. So these two are pretty identical. So 180 nano, 15.5. Okay. So I run it. Okay. And I plot the output at the output node. Okay. Right. Yeah. So what is the DC gain? Look at 0 hertz or 10 hertz, very low frequency. What is the DC gain? 23.27 dB. Is it greater than 10? Is it greater than 10 V by V? Can one of you please confirm?
Yes.
Okay. So what is the unity gain frequency? 0 dB. So wherever this is cutting 0 dB. Okay. This is 1 dB. Yeah. Yeah. See, almost 0 dB, minus 33 milli dB is almost 0 dB. What is the X value? See at the top.
100 megahertz.
100 megahertz. My unity gain frequency is also. I think we can introduce traces. Okay, I'm not sure. Trace. Cursor. Where? How do we get cursor? See, yeah. Zoom to fit. View data points. Okay, this is the points that, anyways, right. So look at this plot. The dashed plot is nothing but frequency plot. Okay. See, initially it started with how many degrees phase shift? 180. Okay. And at 135, you will get your pole. Okay. Where is my 135, 135, 135? So 135 is occurring somewhere here. Yeah. What is my pole frequency? Almost. What is X value? What at the top?
6.55
megahertz. That is where my pole is occurring. What is that value? GM by GDS1 plus GDS2. Yes or no?
Yes.
You can cross check. You know our GM 628 micron. GDS1 plus GDS2 both are equal 25. Okay, so 628 divided by 50 micron. So roughly the same, right? 6 point something you get. So you are getting 6.558 over here. Like I told you, right? The
That is
phase
coming
plot,
as
wherever the 45
12.
degree variation is there, that is your pole frequency. Okay, or minus 3 dB, you can calculate the minus 3 dB as well. So this is 23, wherever you get 20. Wherever you get 20 roughly. Okay, so 23.6, 20.6. So roughly that is also your pole frequency. Minus 3 dB also you can calculate. Okay, right? Is that clear? We are meeting all the requirements, right? Both gain and bandwidth, both are met.
Sir, for pole
Yeah.
frequency, if we use the formula GMO divided by GDS plus GDS2, it is coming as 12.5. So
12.5. 12.5 is it?
yes. So we have to divide 628 by 50, right?
By 50, because both both GDS we took as same, right?
Yes.
So 50. So we are not getting the right value for pole, is it?
Yes, that is coming as something else.
Okay. But minus 3 dB is also coming to be around minus 6.5 megahertz. 20.6. Yeah, 20.6 is also 6.5 megahertz. I'll check once. Why that variation is there. I think 628 divided by 25 micron GM by GDS. 1 second. Okay, that is in other laptop. Okay. Or I might have given the expression. My expression might be wrong. Let me check. Okay. Right. So is this clear, everyone? How to we leveraged the curves for both NMOS and PMOS? Okay. We did it only once. The characterization of the curves is done only once. We are using them several times and solving so many problems. Okay. This is typically used in industry for sizing, this GM by ID methodology. First characterize the entire technology, have the curves ready, have the solution space ready. Okay, so fix a length. So for that length, if you are able to meet the requirements, well and good. If that length is not giving you results, go to higher length 360 nano. Okay, 540 nano, 720 in that fashion. Is that fine?
Yes.
Okay, any doubts?
Sir, how did you plot that graph? How we can do that?
Which plot?
That frequency versus
AC analysis. You have to run an AC analysis. This one.
okay, and then how we can add that graph curves in the plot?
Once you run it, you get a. Let me close it. Again, it is different on Mac and it is slightly different on Windows. Okay, so
Yes.
this is like compiler directive. So you can say draft spice directive. So sorry, not compiler directive. I'm talking about C. Okay, so spice directive. If you are in Mac, you can directly say .ac, dec, and so on. So it will simulate with respect to whichever voltage source you have given AC as 1. So this is the only voltage source where you have given AC as 1, right? So it
Yes.
knows the input node and output node is given to you. Okay, so this probe that you see, the multimeter probe, so this is to select the output. So then it will calculate 20 log V out by Vn and then plot the things for you. Okay.
Okay, yeah.
Yeah, see this .op actually gives you so spice error log. Yeah, see it gives you the operating points actually. Okay. So M1 VGS is 800 anyways, we provided that. See M1 GM is 638 micron, almost roughly there, right?
Yes.
Okay. So this is GDS is not what we intended, but I think M1, M2, M3, all the GDS values also you could see in the error log. So the same in Windows also, but you'll have somewhere here in the options. Okay. So whether your values are coming or not, you can see them over here, the operating points. At least if you are in Cadence, of course, you will have the entire entire thing up for grabs. You can even simulate all these right in Cadence, so that wouldn't be a problem. But yeah.
GDS is also approximate correct, right? It's 27 micro.
27 micro. Yeah, I was not satisfied with this. I don't know why. Yeah, maybe that is the reason why it was causing the pole frequency to be. Yeah.
Yes, M2 for M2 it's not meeting.
Yeah. For M2 it is not meeting. It is 16 micron.
Sir, current is also deviating into M2 and M3 bit.
Yeah, ID is it?
Yes, it if we are using current
See,
bias,
at that point, what happens is 180 nanometer VDSs will be slightly different, right?
Yes.
Because I am applying a signal here. So the VDS of this MOSFET and VDS of this MOSFET will be slightly different. Yes or no? So that causes a change in the bias current. Anyways, I'll explain current mirror in very much detail. Don't worry. In the next class, I'll do that. Okay. So that small variation because of that will be there. So we can rectify this actually by going for a cascade current mirror. Okay. So all those I'll explain layer by layer next class. Okay. That variation will be there because VDS and channel length modulation is there. But a small variation, 8 micron, 8 microamps, a small current.
Yeah, yes.
Okay, any doubts? Yeah, I am done. I'm tired also. Yeah, any doubts? I'm available. I'll be available till 12:30. Else I am done.
So sir, when we get the lab assignments?
Assignments I'll upload today itself. 2 assignments I'll upload. I'll give 1 month time. Is that fine?
Yes.
July 4th, August 4th. Is that fine? Or August, that Monday I'll give you. Okay. So tool is your choice. Cadence or LT Spice. You should understand that. Okay. I told you multiple times the philosophy. Yeah. Okay. Tool is of your choice. Okay. But final exam, lab exam will be based on LT Spice only because we don't have 150 odd cadence licenses. Okay. So lab will be based on LT Spice. So even if you are practicing on cadence, commercial tool, which is very good, also practice on LT Spice so that you can perform in the exam.
Okay. So can you give some bit idea on the how lab exams will happen?
Same. I'll give the similar design from whatever we discussed, whatever labs we have done. Okay, I might give you common source amplifier with a resistive load or a common source amplifier with a active load. So I will give you DC gain, I will give you bandwidth or unity gain frequency and ask you to come up with the sizing of M1, M2, M3 based on the GM by ID curves. Okay. So
Okay,
you
so
have to do you have to do the write up. Okay, so how did you identify W by L of M1? How did you identify W by L of M2? Okay, and then attach the screenshots of simulation. Okay, so you can have this ready. You want to save time. Anyways, from whatever you have performed in labs, those circuits only I'll ask in the exam. Okay, so that you will also be at a comfort level. Okay, and all you have to do is understand that GMID methodology and convince me why you are sizing M1 in that way, M2 in that way, and M3 in that way. That's it. That is what I am testing.
Okay. And
will happen at the center or where it will be?
Online only, online. Okay, so we'll decide on one day. Okay, so all of us need not even meet on the teams. Okay, suppose one particular date 10 p.m. to 10:45 p.m. or 11 p.m. You give me the time what works for all of you. Okay, in that slot, I will upload that particular exam question in LMS Takshila portal. You have to log in and check the question and then answer it accordingly. Okay, so typically I tie the question to your roll number. Okay, suppose if your roll number ends with so and so number, this is the gain and this is the bandwidth. Okay, so that you will have some. I typically make sure that there are 10 to 15 variations in the questions so that mass copying is prevented. So if one of you cracks the question, all of you get it right. So I typically tie the question to your ending digit or ending two digits of your roll number. And then so that we have 15-20 variations and then mass copying is not there. So we proceed in that way. Is that fine?
yeah, yes. And sir, for the if we are performing the cadence, we have to plot the this GM over ID graphs first for the GPDK, and then we can observe, right?
Yeah. So create one, what do you say? That library manager, create one schematic only for these curves.
Okay.
Okay, and its own mastro. So you will have that handy. So whenever you want to size, you can refer to those curves immediately. And all the labs like common source amplifier with resistive load, you can make it another schematic. Okay, so you'll have the curves handy. You have to do that for both PMOS and NMOS.
Okay.
If it is LT Spice, I have done the grunt hard work for you. Okay, you have to invoke MATLAB and use the code. I'll upload the MATLAB code as well today. Okay, and I'll upload lab 2, lab 3 assignment today. Deadline will be 1 month. So lab 4 is today's lab. I'll give it with a 2-week break. I'll again give 1 month time, maybe August 15th, maybe till August 15th. Okay, is that fine? Is the timeline fine by everyone? I didn't want to bother you because you guys were having exams within 2 weeks, so I didn't upload the lab assignment. Anyways, now we have 8 weeks to go, so we have good enough time to do the lab experiments as well. Are the timelines okay? Lab 2 and lab 3, you'll get 1 month. Lab 4, that is what we have done today. I'll upload after 2 weeks and give 1 month again. Is that fine?
Yeah, yes.
Yeah. Someone also had a doubt.
Sir, I have a doubt regarding the exams. So after choosing this exam and the makeup, I found I think paper are a bit difficult in the makeup. Is that true or how is that? Because when I saw analog paper in the regular, it was a bit easy
No,
compared to
see,
the.
except for first question,
Mhm.
everything else was the same, whatever I told you. See,
Yeah,
second question
yes.
I told you is from the problem. Third question is the small signal. Fourth question is this thing. Fifth question is this thing. So it followed the template except for the first question. I think in makeup you got some derivation. Okay.
Yes.
So except for that, everything was the same.
Yes, sir. That was like for first regular paper, it was a easy peasy question where only regions was asked.
See, you have to think about me also.
Yeah.
We will be asked to upload 4 papers.
Okay.
Okay. See, I am not a question paper factory, right? Although LLMs are there, I still have to be very careful in framing the questions. I can't give random numbers also because MOSFETs have to be in saturation. So it takes some time to make the question papers as well. So in that pressure, okay, some deviations I might have done. But I felt I followed the same template, whatever I discussed with you guys.
Yeah.
Apart
The
from the first
maximum.
question, I understand I deviated, but the other 4 questions were from whatever format that we discussed.
Yes.
Okay, you have to cut me some slack there. Else,
Mhm.
2, 3, 4, 5, I felt both are of same degree of complexity in both regular and makeup. Okay.
Yeah.
So somehow you guys listen to your seniors and they say that makeup paper is extra, what do you say, difficult. It is maybe playing in your mind, but I tried to be give the same complexity across both regular and makeup. Okay.
Yeah. Okay, sir.
Mhm. So I was allotted a TA. He is correcting the papers. Okay. I asked him to be generous only. Don't worry. Okay.
Yeah, sir. Okay.
Right.
Thank you.
Thank you.
Sir, on the exam part, there is one question on the source degeneration. So if we take PMOS or NMOS, both are fine, right? There is no mention that
There is
design
no,
with the PMOS, NMOS.
it is up to you. Up to you. Why? If it is
Okay.
NMOS, it is better. Why? Because it won't have a body effect. Right?
Yes.
Because it is towards the ground. I wanted you to replace RS with something, right? Okay.
Yes.
So NMOS would be a better choice because no body effect. Okay. But if you do it for PMOS also, it is fine. Small signal picture doesn't change, right? Remember.
Yes. I
Yeah.
checked that both small signal pictures were same.
Same. It will be same. Yeah. Right. Okay. Yeah. Thank you all. Thank you for joining.
Thank you, sir. Sir, one last
Yeah.
last query.
Please.
Can we get answer key if we want to check
Yeah,
at our end?
I have to give. I'll float the answer key today.
Okay, sir. Thank you so much.
This slides I floated. Okay, answer key also I'll float.
Okay, sir. Okay. Thank you, sir.
ঠিক লাগছে মানে একটা নতুন জানা করাচ্ছে, তো আমি এখন থেকে কি করে বলবো যে ঠিক বা বাজে?
Naveen sir.